So it says in part A, what's the tangential speed of a person living in Ecuador, a country that lies on the equator? So let me get something here. Since I'm podcasting it, I want my picture to look pretty. All right, so let's say that this is the Earth. And if I were at the equator, I'm going to be right there. So the only place where I can use the radius of the Earth is at the equator. Anywhere else, the circle that a person would be moving through is going to be less than the radius of the Earth. At the equator, we can use that. So this number right here, I can use the radius of the Earth for part A. So it says, what's the tangential speed of a person living there? So tangential speed is v. So we're looking for v. So v is our unknown. When they ask for tangential speed, they mean v, and that's meters per second. The r is going to be the radius of the Earth for this problem. And the radius of the Earth is 6.38 times 10 to the 6th meters, and we need the omega so that I can get the v. That's the formula that allows us to go from something angular to something translational, or translational to angular. When I say translational, I mean either linear, tangential, anything where the center of mass moves through space. So the omega in this problem, well, we know they're saying that the Earth turns on its axis once every 23.9 hours, which really, I mean, we sort of usually would just use 24 hours, but we'll use the number that they say here. So we're saying 1 rev every 23.9 hours, and we want to get that in what units? Radians per second. So that means I need to convert revolutions into radians, and I need to convert hours into seconds. 1 hour is 3,600 seconds, and 1 rev is 2 pi radians. So if we solve that, what do we get for the angular velocity? 2 times pi divided by 23.9 divided by 3,600. So we're talking about a small number. .3. What's after that? What? 3 significant digits? 7.30 times 10 to the what? -5 radians per second. So I have all the numbers that I need. Plug it into the formula. V equals r omega. It doesn't have to be rearranged because v is what we're looking for. So we're going to put in 6.38 times 10 to the 6th meters. And we're going to multiply that by 7.30 times 10 to the -5th radians per second. Again, we can ignore the radian here because this really means that's what 1 radian is for this size circle. So meter, if I wrote it per radian, the radian would cancel that. So I will get my answer in meters per second. And what do you get for that? $465.7, so 466 meters per second. All right, any questions with that? So that was part A. Now the hardest part here is B. I'm going to use the same circle that I have here, but I'm just going to show you the difference between, at the equator compared to any place else. If I were right at the North Pole, I'd be right on the axis of rotation, and there would be no, I wouldn't have a tangential velocity because I wouldn't have an r. I'd be going around like this. So I would be still rotating, but I wouldn't be moving through space. Right? I'd be moving around my center of mass. So in part B, we have at what latitude is the tangential speed 1/3 that of a person living in Ecuador? So we want the v to be 1/3 of what it is. So we know what that number is. I can just take this number right here and divide it by 3, and that's what I need it to be. So I know if it's going to be less, then it's going to be someplace closer to either the North Pole or the South Pole. And it's not saying, so we could say the latitude north or south, it's going to be the same thing. But I'm going to have, it's going to be somewhere up here, let's say. So if I drop a line straight down to there, then this right here now represents the R that I would be traveling through. And I know what this number right here. This number is still the radius of the Earth, because there's the radius of the Earth. So going from the center of the Earth to its surface, no matter where I go, if we consider the Earth as a perfect sphere, then we're going to be the same distance no matter where we are. So if that's the radius of the Earth, that's the radius of the Earth. So I know what the radius of the Earth is. If I were to know this number, I could figure out the angle, because all I need is to know two sides, and then I can solve for the angle. So I need to solve for R in this problem. So the omega isn't going to change, and the v is going to be 1/3 of what it was. So if I solve for R, so if I take the equation right here and rearrange it to solve for R, R is going to be V over omega. So this is part B that I'm doing here. R is going to be V over omega. So the V is 1/3 of 466 meters per second. So whatever that number is, what is that number? It's going to be 100 and something. 155.3. So 155 to 3 significant digits. So 155 meters per second divided by, we already calculated the angular velocity in radians per second, so I don't have to redo that. -5 radians per second. And that's going to give me the R, which actually will be, the R will be 1/3 of what it was, right? I mean, if you look at it and look at the numbers, R and V vary directly. So if I have 1/3 of the V, I have 1/3 of the R. So I should just be able to take that number and divide it by 3, and that should be the same answer that I get down here. So if I'm looking at this and dividing that by 3, it looks like it would be like 2.12 something. So my guess is that this is about 2.12. Is that what it is? So the radius is 2.12. Actually, it would round to 2.13, right? It would be closer to that, because it would be 2.126. So it's going to be 2.13 times 10 to the 6th meters. And so now what I have here is I know that amount and I know that amount. Well, what side of this is the angle that will give me the latitude. Because when you figure out latitudes, like if you look on a map and if you're at 10 degrees or 20 degrees north or 30, it's based on 0 is at the equator. And then we go up 10, 20, 30, 40, 50. It goes up until it's 90 when we'd be right at the North Pole. So if I know this number and I know that number, that's the angle that I want. That's going to be the latitude. So what trig function will I use? What's the trig function that I use? Now again, you were all supposed to have done this as part of the problems that I gave you. I should have somebody giving me this answer. What trig function is it? So you're telling me that you didn't do it? What's the trig function? That's the angle. That side I just solved for. That's the hypotenuse. What side is that? Is that the opposite or the adjacent? It's the adjacent. And that's the hypotenuse. So what trig function am I using? Cosine. And I'm looking for the angle. So the angle is going to be the inverse cosine of my r divided by the radius of the earth, because the r is the adjacent and the radius of the earth is the hypotenuse. So that's going to be the inverse cosine of, actually, think about it. This number we know is 1/3 of that number. So really, all that work that I did, I could have just put in 1/3. Because that was the difference between them. That this number right here is 1/3 of that number. So what does that come out to be? Hopefully it comes out to be 70.6. 70.53. Okay, so I guess how numbers are rounded off would make a little bit of a difference. So 17.5 using 1 and 3. All right, so that is part B. And then in part C it says, what's the tangential speed of a person living in Boston located at 42? So now what they're doing here is they're giving me the angle. Now if I know the angle and I know the hypotenuse, I can use that to now solve for the r for Boston, what our r is. We already know the omega, and we'll be able to solve for v. So I need to do a trig problem to get what the r is in Boston. And we know the angle is 42 degrees. So notice I know the angle, and I know the hypotenuse, and I'm solving for that side. So again, what trig function am I going to use? Cosine. It's going to be the hypotenuse times the cosine of the angle. And the angle is 42 degrees. So it's going to be, use a different color, it's going to be that the r is going to be the hypotenuse, which is the radius of the earth, times the cosine of the angle. And so that's going to be 6.38 times 10 to the 6 meters times the cosine of 42 degrees. Is that what it was? 42. And what does that equal? Two minutes left, so. .74 times 10 to the 6th meters. And so they want the tangential speed, which is the v. So you'd be using the formula v equals r omega again. So I'm going to put in 4.74 times 10 to the 6th meters. And I'm going to multiply that by the omega, which we solved up above. That's not changing. 7.30 times 10 to the negative 5th. So 7.30 times 10 to the negative 5th radians per second. And that will give us what the tangential speed is of a person in Boston due to the rotation of the Earth. And what does that come out to be? 346? 346. So at the equator, it's 466. In Boston, where it's at a latitude of 42 degrees north, it's 346. So it's less because you're moving through a smaller circle. Even though both places, we're moving at the same angular speed. We're at the same angular speed, but different tangential speeds.